Hi, Assalamualaikum and good evening. My name is Muhammad Azim bin Muazzin with matrix number of TP24020. This is a video presentation for sensors and instrumentation systems. The title that we choose for this project is Unplanned Downtime Due to Critical Motor Failure. This is a video prepared by our groups. So, without wasting any time, I will jump straight to the problem statement. The problem that we had is the unplanned downtime due to critical motor failure. In a manufacturing environment, electric motors such as those in driving conveyor, as you can see on the picture that I put on the slide, conveyor belt or CNC machines are the heart of production. A major challenge is the sudden catastrophic failure of these motors without any prior warning. So the issue that we had is a failure of often stem from internal mechanical degradation such as bearing wear, shaft misalignment or stator winding faults. These issues are invisible to naked eye and cannot be detected through routine visual inspection until it's too late. Another issue is related to the sensor. The problem is fundamentally a sensing gap existing system to fail to detect a micro changes in vibration signatures and temperature anomalies at an early stages. Without high precision sensor, these subtle indicators of wear go unnoticed before evolving into a critical failure. And we jump straight to the impact on production and quality. There are three of them. The first one is a production halt. Sudden breakdown leads to the immediate unplanned downtime, causing significant financial losses. Every hour, the line is very stagnant. Second is a safety risk. Extreme motor failures such as overheating or mechanical fragmentation pose directly physical risk to operator on factory floor. The third one is a product defects. Unstable motor vibration before a total shutdown leads to a machine's inaccuracy. Misalignment, cast, or improper assembly is the example, compromising the quality of the final product. I think that's all from me. The rest will be continued by my group members. Thank you.
Okay, for the method for current system, sometimes we use temperature sensor RTD thermistor to detect the motor heat, and also use current sensor to detect any overload or abnormal power usage, or sometimes the motor when it's broken it will drain more power, so we can detect from that. And some machine also include basic vibration sensors. So when the motor vibrate unnormally, it will show the the problem. And also, instead of that we use maintenance mainly relies on periodic manual inspection by technician. Sometimes it's scheduled checking, such as once a month or twice a month. Okay, but the weakness for this method is sometimes we cannot detect any early or stage fault like a small bearing wear or slight misalignment. We only detect when the problem is too big, and the temperature and current change only appear when damage is already serious. So if we detect the damage from the temperature, the motor is already at a broken stage. And limited real time monitoring depends on manual checks. Also, basic vibration sensor cannot capture small vibration change, such as because it's low sensitivity. So if any small change, it cannot detect, and maybe at the long period time, the motor will damage. And this also result in unexpected breakdown, downtime, and higher maintenance cost. If a motor broken, it will be a breakdown, and the company will stop production, and it also will cost from the maintenance and also the sales. Okay.
Now I will present the proposed improvement to solve the motor failure problem. The solution is an IoT-based predictive maintenance system that focuses on early fault detection using smart sensor and data analysis. For the proposed technology, this system uses high sensitivity vibration sensors, specifically MEMS accelerometers, to monitor motor condition. It is connected to an IoT platform for real-time monitoring and use AI or machine learning to predict possible faults. Unlike the current system, it operates continuously without manual inspection. Next, the sensors collect real-time vibration data from the motor during operation. Each motor has its own normal vibration pattern. When a fault starts to develop, even at a small level, the vibration pattern will slightly change. This change is captured and sent to the monitoring system. The collected data is analyzed using techniques like fast Fourier transform or FFT. This helps detect change in frequency, amplitude, and wave patterns. AI algorithm then identify abnormal signals and predict potential failures early. Next, why this solution is better? This solution is better because it can detect faults at a very early stage. Even before major damage occurs, it is more sensitive than current sensors, provide real-time monitoring and reduce delay in detection. Most importantly, it predicts failures before they happen. In conclusion, this system solves the sensing limitations in the current setup. It changed maintenance from reactive to predictive, which improve motor reliability and overall system performance.
Okay, so now I'll be talking about the benefit. The first benefit is elimination of the sensing gap. By utilizing industrial grade MEMS accelerometers, the system can detect micro level change in frequency and amplitude that are invisible to the naked eyes. This allows for the identification of early stage bearing defect and shaft misalignments that existing low sensitivity sensor fail to capture. So benefit number 2 is drastic reduction in unplanned downtime. The ability to predict potential failure before they become critical shift the maintenance strategy from reactive to predictive. This prevents sudden breakdown and avoid the significant financial losses incurred during very hour of production line is stagnant. Okay, benefit number 3 is protection of product quality. Early fault detection ensure maintenance is performed before unstable motor vibration cause machine inaccuracy. This prevents misaligned cuts or improper assembly, maintaining high quality for the final product. Okay, the last benefit is enhanced operational safety. By preventing extreme motor failure such as overheating or mechanical fragmentation, the system directly reduces physical risk to operators and the factory floor.